This lecture is going to be the first over chapter 27. We're going to be dealing with sections 27.1 and 27.2. We're going to explore the concepts with relativity and simultaneity. And this is going to be something that is a 20th century development of physics. Up to this point, we have been looking at developments from the 17th and 18th centuries regarding movement of objects, regarding electricity, magnetism, optics, things of that sort. Around the turn of the century is when you start to see developments within the realm of physics that allow us to be able to conceptualize what's going on in environments that are outside what we commonly perceive. And relativity is an explanation for when you start to approach the speed of light. So as you can see here in the summary, all of the fundamental laws of physics have the same form in all inertial frames of reference. Inertial frames of reference, we are looking at frames that are not, they may be moving at a set velocity with each other, but one is not accelerating with a relative to the other. So they may be moving at constant speeds or velocities, but they're not accelerating. So that is, if they start to accelerate, then we're looking at non-inertial reference frames. So when it comes to Newtonian mechanics, you're looking at inertial reference frames. I want to make sure that you've got that idea. The speed of light in vacuum is the same in all inertial frames of reference and is independent of the motion of the source, which in other frames of reference, if we look at things other than light, that becomes somewhat quizzical. The relative motion in the speed of light, if you're moving, then you would think that your motion relative to the light would cause that velocity to slow down. But that's one of the pillars here of relativity. Simultaneity is not an absolute concept. Two events that appear to be simultaneous in one inertial frame may not appear simultaneous in a second frame of moving relative to the first. So let's take a look at the sections here in depth. So, fundamental postulate, special relativity. All the laws of physics, including mechanics and electromagnetism, are the same in all inertial reference frames. So suppose you watch two children play catch with a ball while the three of you are on board a train that moves with constant velocity along perfectly smooth tracks. Now suppose you want to estimate the speed of the train without looking out the window. Might be tempting to follow the motion of the children's ball in order to deduce the speed of the train. However, you find that no matter how carefully you study the motion of the ball, you couldn't tell how fast or in what direction the train was moving. And this is because the laws of mechanics are the same in every inertial system. Another example is going to be the EMF induced in a coil of wire by merely moving permanent magnets. By a nearly moving permanent magnet. A nearby moving permanent magnet. Well, I'll get that right. In the frame of reference in which a coil is stationary, the moving magnet causes a change in magnetic flux through the coil. And this change induces an EMF. In a frame of reference in which the magnet is stationary, the motion of the coil through a magnetic field causes magnetic forces to act on the mobile charges in the conductor, including inducing an EMF. And according to the principle of relativity, both of these points of view have equal validity and thus predict the same induced EMF. Faraday's law of electromagnetic induction can be applied to either description, and it does indeed satisfy this requirement. If the moving magnet and moving coil situations did not give the same results, we could use this experiment to distinguish one inertial reference frame of another, and that's not something that we observe. So you've got a magnet that is moving relative to the coil, and then you've got a stationary magnet here, inducing experiments using a magnetic field moving relative to the coil, and then a stationary magnet. So equally significant is the fact that Maxwell's equations predict the speed of electromagnetic radiation. You may not remember that, but that was derived earlier, back in chapter 23. The laws of electromagnetism show that light and all other electromagnetic waves travel with a constant speed, and there it is. And so we'll often say 3 times 10 to the 8th meters per second to round off. That is within 1 part in 1,000 of the exact value. Now, if these laws are the same in all inertial reference frames, then the principle of relativity requires that the speed be the same in all inertial reference frames. So, during the 19th century, most physicists believed that light traveled through a hypothetical medium called the ether, just as sound waves travel through the air. And if that were true, the speed of light would depend on the motion of the observer relative to the ether and would therefore be different in different directions. But the Michelson-Morley experiment was an effort to detect the motion of the Earth relative to the ether. Einstein's conceptual leap was to recognize that if Maxwell's equations for the electromagnetic field are to be valid in all inertial frames, then the speed of light in a vacuum should also be the same in all inertial reference frames in all directions. And in fact, Michelson-Morley detected no motion of the laboratory relative to the supposed ether. And indeed, there is no experimental evidence for the existence of an ether, and the concept has since been discarded. And I don't know if you've been introduced to that concept before or not. So a direct consequence of Einstein's principle of relativity, sometimes called the second postulate of relativity, is that the speed of light in vacuum is the same in all inertial reference frames and is independent of the motion of the source. So let's say you've got 2 observers measuring the speed of light. One is at rest with respect to the light source, and the other is moving away from the source. Both are in inertial frames of reference. According to the principle of relativity, the 2 observers must obtain the same result for the speed of light, despite the fact that one is moving with respect to the other. So let's say we've got a spaceship that is moving past Earth at 1,000 meters per second, and it fires a missile straight ahead with a speed of 2,000 meters per second relative to the spacecraft. What is the missile speed relative to the Earth? It looks like it's a pretty elementary problem. The correct answer, according to Newtonian mechanics, is 3,000 meters per second. But let's suppose that there is a searchlight in the spaceship pointing in the same direction that the missile was fired. An observer on the spaceship measures the speed of light emitted by the searchlight and obtains a value c. According to our earlier discussion, the observer on Earth who measures the speed of the same light must also obtain the value c, not c plus 1,000 meters per second. And that contradicts our elementary notion of relative velocities, and it may not appear to agree with common sense, and it's a break from what Newton would say. But common sense is intuition based on everyday experience, and such experience does not usually include measurements of the speed of light. So let's restate the argument symbolically using 2 inertial frames of reference, labeled S for the observer on Earth and S prime for an observer on the spaceship. So we're going to omit the z axes here in order to be able to better describe what's going on. The x-axis of the 2 frames, this direction, lie along the same line, but the origin of the frame S moves relative to the origin of S prime moves relative to the origin of frame S. With constant velocity, that's the key there, is these are inertial reference frames, so they're moving at constant velocity along the common x minus x prime axis, or x prime axis. We set our clocks so that the 2 origins coincide here at time t is equal to 0. And then their separation at a later time t is u times t, because u in this particular case is velocity, constant velocity. So a moving coordinate system here is showing that the position of particle P can be described by the Earth coordinate x and y in S, or by the spaceship coordinates x prime and y prime in S prime. Now, how do we describe the motion of the particle P? It might represent an exploratory vehicle launched from the spaceship, a flash of light from the searchlight, what have you. We can describe the position of point P by using Earth coordinates or spaceship coordinates. And this figure shows that these coordinates are related by the transformation equations of this and this. Since it's not moving in the y direction, we're not looking at any sort of velocity there. We're going to reduce this down to a one-dimension change, or change of velocity in one dimension, just to make it easy. So we're going to add the assumption that not all time measurements are the same in the two reference frames. Or we're going to add the assumption that all time measurements are the same in the two frames of reference. Sorry. These three equations are going to be based on the familiar Newtonian notions of space and time, and are called Galilean coordinate transformations. So if point P moves in the x direction, its velocity v, as measured by observer who is stationary in S, is given by this, and its velocity v prime, measured by an observer at rest in S prime, is going to be this. From the discussions of relative velocities way back in chapters 2 and 3, we know that the velocities are related in this fashion. What's the velocity that you are seeing in frame S is going to be given by the velocity in S prime plus the rate at which these reference frames are moving with each other. And so if you take that and you extrapolate it into changes in X, and then you can see that here, and that's where this comes from. So here's the fundamental problem. If we take equation 27.2 to the speed of light, using c for the speed seen by the observer in S, and c prime for the speed seen by the observer in S prime, then this is what it's going to say. And Einstein's principle of relativity, which has been supported by experimental evidence, says that those two have to be equal. And so, yes, that is a genuine inconsistency, not an illusion. And how do you explain it? So if you accept the principle of relativity, we're forced to conclude that these, appealing as they are, cannot be correct for the speed of light and are not consistent with the principle of relativity. So you've got to reconcile the two. So what we're going to have to do is we're going to have to modify our concept of kinematics. And the obvious assumption that we want to look at first is, do both S and S prime share the same time scale? We stated this assumption formally by including it in equation 27.1, but we're about to show that the assumption that T is equal to T prime cannot be correct. The two observers must have different time scales, as if you needed something else to worry about. So how do you relate the two? So what we're going to do is we're going to go through a bunch of thought experiments, or in Einstein's original German, Gedanken experiments. Don't clarify that. Okay. So when two events occur at the same time, we say they're simultaneous. If you woke up at 7 o'clock, then two events, your awakening and the arrival of the hour hand of the clock up to number 7, occurs simultaneously. Fundamental problem in measuring time intervals is that in general, two events that are simultaneous when seen by an observer in one frame of reference are not simultaneous as seen by an observer in a second reference frame if it is moving in relation to the first, even if both are inertial reference frames. This is the relative nature of simultaneity. This idea may seem contrary to common sense, but here's a thought experiment. Consider a long train moving with uniform velocity, and two bolts of lightning strike the train, one at each end. Each bolt leaves a mark on the train and one on the ground at the same instant. So the points on the ground are labeled A and B, and the corresponding points on the train are A prime and B prime. An observer is standing on the ground, midway between A and B. Another observer is at O prime, at the middle of the train, midway between those two. Both observers see both light flashes emitted from the points when the lightning strikes. So inside the train, Julianne moves towards the light coming from the front of the train and away from the light at the back of the train. And because Julianne sees the light at the front of the train first, she believes that the lightning at the front of the train hit first. Justin sees the light hitting the 2 points at the same time. He believes that the lightning hit the front and the back at the same time. And at this point, the light from the lightning strike at the rear of the train has not yet reached Julianne. So you can see here, basically a recap. Suppose the two light flashes reach observer at O simultaneously. He knows he's the same distance A as from B, so he concludes that the two bolts struck A and B simultaneously. But the observer is moving to the right with the train with respect to the observer at O, and the light flash from B reaches her before the light flash from A does. So she's moving in this direction. The light from here reaches her first, then the light from here. Because the observer at O is the same distance from A prime as from B prime, she concludes that the lightning bolt at the front of the train struck earlier than the one at the rear. Two events appear simultaneous to observer O, but not to the observer at O prime. A subtle but important point in this example is that there is no measurement that the train passenger could have made that would have concluded that the lightning strikes were simultaneous. So in other words, information, whether regarding lightning strikes or anything else, cannot travel faster than the speed of light. So whether two events at different space points are simultaneous depends on the state of motion of the observer. So furthermore, there's no basis for saying that O is right and that O prime is wrong or the reverse. According to the principle of relativity, no inertial reference frame is preferred over any other. Each observer is correct in his or her own frame of reference. So in other words, simultaneity is not an absolute concept. Whether two events are simultaneous depends on the frame of reference. Because of the essential role of simultaneity in measuring time intervals, it follows that the time interval between two events depends on the frame of reference in which it's measured. So the next task is to learn how to compare time intervals in different frames of reference.